Last night at a bar, one of my friends challenged me to the classic "What are the odds" games if I would get the number from the waitress. It was 1 to 5, and those are reasonable odds, but it got me wondering, what are the actual odds, statistically speaking? We played 1 to 5, but what if you went 1 to n? So player B is daring player A to do something. The game goes, if both players guess a random number between 1 to n, if it's the same number the players guess, then player A loses. If the numbers that are randomly guessed add up to n, then player B loses. It's a simple game. Let's take a look at the actual statistics. I'm going to ask 3 questions here. What are the real odds of A and B losing? Are there any optimal n values that you should pick if you're player B challenging player A? And does player B always have an advantage in the game? Or is there a point where player B actually has a greater chance of losing? Let's dig into the stats here. We can start by just taking the simple scenarios, writing out all the probabilities, and then generalizing to the greater n value. We can start by writing down all the possible combinations of guesses from player A and player B. Here we start with player A guessing 1 and player B guessing 1, then player A guessing 2 and player B guessing 1, and so on to get the complete set of 4 values. Now player A loses in these scenarios where the values are equal. In this case, the chance of player A losing is 2 over 4, so about a half there, and player B has no instances. Now technically 1 plus 1 would add up to 2, but that's the case where A loses, so we don't count that for player B. Of course, this is the optimal solution for player B to pick this, but player A would never willingly accept these odds. Let's go to 1 to 3. Here we have 9 possible pairs. 3 make player A lose, and 2 make player B lose. Here are the odds there. Going now to 4, player A loses in 4 of the 16, about 25% of the time, and player B loses 1 over 8. So a little bit better odds for player B here. Notice also, in the case of 1 to 3 and the case of 1 to 4, there's only 2 possible ways for B to lose, even though when we played 1 to 4, there was 16 possibilities instead of the 9 possibilities in 1 to 3. You can see there might be an optimal value here for player B to pick something. One more scenario. Let's look at 1 to 5. Here we've got 5 potential ways for A to lose, and B can lose in 4 ways out of the 25 possible. Let's try to generalize these results now. Here they are laid out, and we want to know what's the general percentage for A to lose and B to lose for 1 to n. We start by writing out these general forms using the numbers that are present in each of the situations. So we're going to use 2 here, 3s in here, 4s in here, 5s in here, and you can see that some patterns will begin to show themselves. Just take a look at the A lose. For 1 to 2, it's just 2 over 2 squared. Then it's 3 over 3 squared, 4 over 4 squared, 5 over 5 squared. That's a pattern clearly. So we know that the A lose will be n over n squared. But the B lose is a bit more complicated. Look at the B lose row. The denominators are always 2 squared, 3 squared, 4 squared, 5 squared. That's confidently going to be the denominator of n squared. But the numerators are very weird. You've got 0 in the case of 1 to 2. In the case of 1 to 3, we go to 3 minus 1, and then it's 4 minus 2, 5 minus 1. It's a bit odd, but you can maybe pull out a pattern here. And it starts by rewriting that first column for 1 to 2 as 2 minus 2. And then we'll see, take a look, in 2 cases we have a minus 2, and in 2 cases we have a minus 1. With the purple arrows, we're doing even numbers minus 2, and with the green arrows, we're doing odd numbers minus 2. Odd numbers minus 1. So thus we can split our case here, our general form, into when n is odd, B lose will be n minus 1 over n squared, but when n is even, B lose will be n minus 2 over n squared. So this will be our general form. We can take this now and apply it to a general game. Let's say someone wants to do 1 to 7. What are the odds? Well, here are the odds. N is odd, so A lose will be 7 over 7 squared, and B lose will be 7 minus 1 over 7 squared, which comes out to a 14.3% chance that A loses and a 12.2% chance that B loses. And now you can take this and apply it to any n value. You can do 1 to 50, 1 to 100, 1 to 200, and you can solve for the chance that A will lose and the chance that B will lose. That answers our first question of what are the actual odds, but for questions 2 and 3, we need to program this and take a look at the graphs and the values over long ranges. I've done this in MATLAB. We'll take a look at that simulation now. Here I've set up a simulation, and we're going to actually do 1,000,000 trials of the game. We've set n to be 4, so we're playing a game from 1 to n, and I've set up some counters here. If you're not a programmer, don't even worry about this. If you are, you can take a look at the algorithm. I'm just going through a for loop for each of the trials, generating the player's random guesses. If A is losing when A equals to B, then we're just counting that. If there's the case when B loses when A plus B equals to n, then we're just going to add in the B loss there. And that's it. Then from here, we're counting the total number of losses over the total number of trials we ran, and that'll give us our simulated results for A, and then here for B. And then I've got my analytical solution here that we took from the general form we just solved for. A is just going to be 1 over n, same thing as n over n squared. And then for B here, we just need to divide between the case of odd and even, and then proceed to calculate the values that we showed previously. So now we can run this for a given n value, and we should be able to get simulated results versus our analytical results. And this will tell us if our model is correct or not. Here we see the probability that A lost as 0.25, and the analytical agrees with 0.25. And then B lost is 0.1249, and the analytical is pretty darn close there as well. The analytical solutions won't change, but every time we run the simulation, the simulated results should, because they depend on randomness. So we can go ahead and run this a few times. We get a 0.08 here at the end and a 1256. But again, they're going to be pretty darn close to the analytical, always varying with the randomness of the simulation. This makes our model pretty confident that it reflects the reality of the game. I can plug in 7 here, and we get the same values that we had calculated previously, and the simulated results agree. This solves it for just one n value, playing one game 1,000,000 times from 1 to n, but we want to see trends over a longer period. For example, how does n equal 2 and n equal 3 compared to n equals 2 and n equals 30? What we can do then is run another for loop in a different approach and loop over the n values. Again, don't worry if you're not programming this, but we're just going to calculate these values now over all these different n values. If we plot this, we'll see the trends here. So we start on the x-axis with the n, playing the game from 1 to 2 or 1 to 6, and in blue we see the odds or the probability that A is going to lose. So if n equals just 2, half the time, 0.5, player A will lose. And then as the number of n's, 1 to whatever, increases, the odds of that player losing actually decreases. If we're playing a game of n equals 20, probability of A losing is only going to be about 0.05, which is 1 in 20, which makes sense. Probability in B losing is actually shown here in the orangish triangles, and you can see when n equals 2, there's no way for B to lose, so that's at 0, and then it jumps up at 3, goes down at 4, and then actually increases when you get to 5. And this harkens back to the notion that on odd numbers, we have an n minus 1, but on even numbers, we have the n minus 2. So if you're player B, you actually want to be guessing the even numbers, because your probability of losing is lower. So if you're going between 3 or 4, player B, you want to choose 4 because your probability is lower, assuming that you want to minimize your chances of losing. There's one more thing we can look at. This just answered question 2, right? There's really no optimal values along this thing. Of course, player B, you should probably get player A to do a n equals 2, but that's unlikely. There's no other maximums or minimas as we go along this, but in general, player B should be choosing even numbers as opposed to odd numbers. There's one more thing we can look at, and that would be the difference of the probability of losing. We can do this by calculating the difference of the probability that A loses and the probability that B loses. And this will show an optimal choice then for player B. If we take a look, we can see that, of course, here at n equals 2, the probability here that A is more likely to lose than B, 50%. That's natural because player B can't lose when n equals 2. But the difference here at n equals 3 goes down significantly and goes up just a little bit at n equals 4. So how much is A more likely to lose than B? In this case, A is slightly more when n equals 4 than when n equals 3. So again, harkens to the fact that player B should be choosing these even numbers as opposed to the odd numbers. You'll notice as n increases to about 20, there's really no difference in the numbers. Really, if you're less than 10, you've got some odds that you can play with, but once you get bigger than n equals 10 and n equals 20, the game really evens out. We can also take a look at this if we plot n going all the way to 200, and you can see the probability of A losing and the probability of B losing essentially become the same. Player A is always slightly more likely to lose, but as you get out here to n equals 200, the difference is some 1/100th of a percent of an advantage for player B. Back to our original questions. Question 1, what are the odds? We defined our general form earlier in the video. Question 2, are there optimal n values? Sort of in those first 10. Of course, if player B can get player A to accept the odds of n equals 2, that's great. Otherwise, just stick to the even values. And then question 3, does player B always have an advantage? Yes, they do. Player A will always have a slightly larger chance of losing than player B. That answers our questions. Thank you for watching. This was a fun video to make. I very much enjoyed calculating these values and getting the general forms. If you appreciated this as well, go ahead and like and subscribe, and feel free to add any comments in the comment section. Have a great day.